Our second speaker today is Toby Smithe, who's going to talk about copy composition for probabilistic graphical models. Please.
Yes, okay, great. That's what I'm going to talk about. Thank you. Right, so what do I mean by copy composition? Well, sometimes we want composition not just to be like this, where we hide this middle thing, but somehow to keep it around. This scares some people, but it's actually quite useful sometimes. And in particular, in probabilistic modeling, often the object we care about is not like the composite channel, which is like the marginal at the end, but the whole set of the things in the middle, which is often called the joint distribution or conditional joint distribution. And here, this is one picture of such a joint distribution. You've got some prior, which is a state, and you keep that around, and you have some channel or kernel, which is your sort of conditional here on y, and that's called a likelihood in lots of settings. And the sort of joint distribution is like the product of these two things. And keeping this wire around corresponds to keeping that product rather than marginalizing out x. Neil just talked about approximate game theory, and last year I talked about a kind of approximation for doing Bayesian inference, which I called statistical games, and it had a very similar structure where you have a game, which is in this case a pair of two things, one of which does Bayesian inference, and a way to measure how good it was, and that's a loss function. It's a bit like a sort of quantitative selection function in game theory. But the loss functions I was interested in, the weird thing about them was that they were only kind of copy compositional. For the rule I wanted to obtain to work, I needed to keep around this middle thing all the time. And I sort of came up with a bicategory ad hoc. It needs to be two-dimensional because you have this extra thing here. But I wasn't very satisfied by that. I wanted to have some kind of structural origin for that bicategory. And I started thinking about it, and this is what this talk is really about. I've got two cases of composition to talk about. One is in what are called directed models in probability theory, often known as Bayesian networks, and another one is in undirected models, and they're kind of similar but kind of different. And I hopefully we'll talk about both, and I'll show some string diagrams, and it'll be nice. Okay, so what is a Bayesian network? I don't have time to give a sort of full definition, but I can give you an intuition. It's a probability distribution that factorizes over a directed graph, and this is why it's directed. The nodes in your graph are like random variables, and then the edges represent conditional dependence in your distribution structure. Brendan Fong, in his master's thesis, showed that any Bayesian network can be written as a composite of certain morphisms of this form, where you've got a lot of wires which represent sort of uninvolved random variables, and some things which represent parents of your random variable in your graph structure, and you feed in the sort of parents, and you do your conditional dependence thing, and you keep around its output, and you keep the whole structure around. But the key part is that you keep the whole structure around, right? You keep the copies of the inputs, and you keep around all the preceding inputs. And so this is inherently like it's a copy compositional thing, but Brendan just like I did, he just constructed this thing by hand. But actually, this thing comes out from a sort of very natural kind of type theoretic kind of perspective. So the first thing to say is that with sets and functions, if you have a function x to y and you precompose it with a copier like this, it gives you what's known as its graph. And the thing to say about the graph is that it's a section of the projection. I mean, this is kind of obvious because if you throw away this x, you get the function again. That's what it means for this thing to be a copier. It has to be this comonoid. And so that means it has to behave well with your deleting. Being a section of this projection means that we could think of it as a sort of type theoretic. We think of it as a term of this product type with x being the context. But this is all, this story so far is all deterministic. It's just with sets and functions. But we can tell the same thing with probability kernels. And so that's what we'll do. But before we do that, I want to say that in that previous diagram for Bayesian networks, I had a bunch of wires that were kind of uninvolved, representing sort of the parents, the sort of non-parents, as it were. And where did they come from? Well, they also come from a sort of standard type theoretic thing, which is called context extension. But that just means pulling back along another projection. And so we've got these two things. One is kind of pulling back along this projection, and one is the fact that these sort of copy composite things look like sections. And sort of the main job really is to sort of instantiate this sort of type theoretic setting in this kind of probabilistic world. And the way to do that is to say, okay, well, what I need is a bifibration, and the bifibration structure gives you both of these operations. Okay, so what I need is a bifibration of probability kernels. We've seen some examples of what a probability kernel is. I say probability kernels, but really I mean something a bit more general than probability kernels, because a probability kernel is a morphism which always emits a probability distribution, and a probability distribution integrates to 1. But I'm going to need them to be a bit more general than that, because I want to have, later I want to have kind of predicates, fuzzy predicates, which are going to be morphisms into the monadic units. And in the case of the probability kernel, those are all trivial. But so to say a little bit more about what a kernel is going to be for me, it's a function from some measurable space and a sigma algebra on another measurable space, which is its codomain, into the positive reals. And these things satisfying some like finiteness condition are known as S-finite kernels. And I'm working with these kernels, but the story I'm telling is not specific to this particular bicategory. I would say in a minute that you can tell this story for a more general setting. But this is to say that we can do this for the probabilistic situation that I was interested in. But okay, so I've said what a kernel is. It's between two measurable spaces. It's one of these functions. It's measurable in the first argument, and it gives you a measure, i.e. a distribution in the second argument. And I want to build a sort of fibration of these. And the way I'm going to work is just by analogy with sets and functions. And you may know about something that's called the codomain fibration, or the arrow category, which has a bifibration structure. And there you have your objects being functions into some base object, which I'm calling B. And these represent sort of, they're bundles. They represent collections of types indexed by some base, or collections of sets indexed by some base. And here I'm going to be doing the same thing for my objects. So I work with measurable functions in my base. And then the morphisms between them are going to be kernels, the sort of kernels fiber-wise, so they preserve this base point. And that means they satisfy this equation. That, if you write it out, it's like a triangle. It's exactly the equation that you satisfy in your sort of slice category. But the difference is that we have this randomness in your morphism. And the key thing that allows you to sort of compose these measurable functions with these kernels is that every measurable function induces a deterministic kernel, and you compose them by something that's called push forward. Okay, and so if you have these kernels which satisfy this kind of equation, this sort of triangle condition, then you can think of them as fiber-wise. To say precisely what I mean by that, I'm going to use this notation that David Spivak uses for pullbacks. So if you've got a sort of a bundle here from P e to B, and some morphism into B, little b, then you can, we write this pullback object as P square brackets B. And you can really easily show that if you've got a kernel satisfying this condition, it restricts to a kernel sort of fiber-wise. That is to say, it restricts to a kernel between the sort of fibers over this generalized element. I mean, it's proposition 2.8 in the paper, but it sort of barely deserves that name. It's very, very easy to show. You precompose your kernel function with these projections on E and B prime, and that's your sort of pullback kernel. Okay, so that's like the main sort of technical slide. I'm going to say a little bit more about like the bifibration structure, but it's really easy. It just comes exactly from the bifibration structure of the codomain fibration of measurable functions. So you get this pullback thing, which gives you a substitution functor. It acts by restrictions on kernels, exactly like this. It's very easy. It gives you the fibration structure. It's contravariant, and then you have a covariant left adjoint to these functors, which gives you what's known typologically as dependent sum, and this just acts on the objects by post-composition. So if you've got some P over J and some B from J to big B, then you just post-compose like this. It's an object. It's really easy, and on the kernels, it just acts by identity. That's nice. And you get an adjunction, which is quite easy to show. I mean, in MES, you have that adjunction, so you just put it forward by this deterministic sort of embedding. And then these satisfy this condition called Beck-Chevalier, which means that if you have a pullback in your base category here, it's measurable spaces and functions, then you can sort of go around your pullback square using substitution dependent sum either way, and it doesn't really matter which way around you go. And we're going to need this for associativity of the composition that I'm going to define.
Toby, can I quickly ask, is there any chance of spelling product?
I thought someone might ask this. Well, no, in the case of MES, you don't even have a Cartesian closed structure. I know that with like some versions of some probability categories, you get a Cartesian closed structure, particularly in quasi-Borel spaces. I thought for a while that I could make a dependent product come out of that structure, and then I got sort of lost in the weeds and didn't finish trying to convince myself it was true, but I sort of thought maybe I could get one, but maybe someone else knows better. But it's not very nice, and I don't want to say that there is, but maybe there are settings in which you could. But it wouldn't work like a sort of stochastic. You would only get randomness in sort of one argument of your products, because there's no way to introduce randomness in two arguments. We can talk more about it later if you want. Okay, so that's my bifibration structure, and I can use this now to do these two operations which I introduced earlier, which are going to give me my copy composition. And so, okay, well, what I really want to do is if I've got a graph of some stochastic function, some kernel, and a graph of another one, I want to compose them in this kind of way where I keep all of the objects around. And the answer to doing this is exactly using these two operations of substitution and dependent sum. It's called pull push, because first of all, you sort of pull back along one projection and then you push forward along another. And to sort of make that really clear, I've drawn this out on the diagram. So if I've got my graph, so I've got these spans which are my projections from my two product objects, and I've decorated them with sections. And what I do is I take my section on the sort of second span, and I pull it back along this projection, and then I sort of push it forwards along the first one, along the first left leg, in order to be in the sort of the right space or the right fiber. And then I can compose these two as kernels, and this gives me a section of this composite thing. And so I said decorated, and really this is a sort of decorated span construction. And so we can use the machinery of decorated spans or decorated co-spans. In particular, we're here, as I said, before I had a bicategory, we're going to have a sort of two-dimensional structure. And so we can use a double Rosen deconstruction perspective on decorated spans and co-spans, which Evan Patterson talked about last year, which is really very nice, and it's quite easy and it's quite general. As I said, if we have a bifibration like this, some bifibration, and we have a section of it, in the paper I show you, you can obtain exactly a double fibration. I call it, blackboard S over spans in the base category, in a slightly annoying restriction that the spans with morphisms of spans, those are your cells in your double category, they have to be sort of Cartesian, they have to be pullback squares in your morphism. And that's to sort of make horizontal composition of squares work nicely. So as we've seen in the previous diagram, we decorate these spans by sections of their left leg. That's what the section of your vibration is for. Horizontal composition is by pull push. It's exactly what I showed you. And then we need this Beck-Chiarelli condition for the associativity. And this does exactly what I wanted, and it's quite nice because it has this sort of type theoretic structure. And in particular, we can recapitulate this sort of construction of Brendan's exactly in the way I said, and so that works very nicely. The way to do that is to say, okay, well, I've got kernels. They embed into this double category in a sort of lax horizontal way, mapping kernels to their now stochastic graphs. And so what we say is, okay, well, now I take my image of this of this factor of my Bayesian network in this, it precomposes it with the copiers, and then I can sort of pull it back along the projection that sort of extends the context by these other objects. And this gives me another section of this whole thing. And then I can compose these in this sort of copy composite way, and this gives me my Bayesian network. So that sort of recovers what Brendan did in a sort of neat kind of type theoretic way. And kind of tentatively, it means that you could sort of think about Bayesian networks where some of your sort of objects, your random variables have like some kind of type dependent structure, which I think is quite neat. You don't see very much in probabilistic modeling where people have dependent types around, partially because I think people don't really think much about these sort of bifibration. But I think it could be useful. Okay, so that was the directed case. How much time do I have left?
10 minutes.
10 minutes. Okay, great. So then let's talk about the undirected kind of models. So these are these are kind of different because you don't really work with kernels per se. You work with some other way of factorizing your distributions. And one of these ways in the sort of modeling literature is called factor graphs. And what these are ways of representing the density functions associated to your distributions as factors of other sort of smaller functions, which may or may not be density functions, but they are just functions. And so sometimes people draw these things like this in this sort of bipartite graph structure where you've got kind of random variables or sort of nodes that represent types, and then factors, which are functions from these objects or the products of these objects into the reals or the unit interval or something like this. And then you form a graph by just taking products of all these functions. And I hadn't seen a sort of presentation of this in a sort of compositional setting, and I was quite interested in inference on these things. That's what I talked about last year. This is what I'm quite interested in generally, approximate inference. But one thing you can notice is that you have a sort of similar copying situation here because you've got A, for instance, that goes into F0 and F1. So you need to copy this A to put it into these. And of course, it had some other compositional structure, which is that you can, these are functions and they could in some sense also contain some factorization. So it has this kind of sort of operatic kind of nesting structure where you have like factor graphs within factor graphs. So how do we like formalize this? Well, I told you about S-finite kernels. They're like kernels which don't have to integrate into one. Now, if you sort of think back to my definition, if you think of what is a kernel into the sort of one element space, if I just skip back a bit, maybe I should have written it out, then it sort of has a trivial sigma algebra in this right-hand factor. And so you could sort of forget about this part, and then you get just functions into the positive reals. And so the sort of co-states in this monoidal category are exactly these factors. And this is quite a common pattern in modeling or in these so-called copy discard categories, where you think of the sort of co-states as predicates in some way. They're sort of like dual to states. They sort of measure, you compose a state with a predicate and it gives you a number. It is to say how good this state is in this kind of logical setting, something like that. There are copy discard categories we've seen a few examples of. There are sort of specializations of this notion. This is just where you have comonoids everywhere, but specializations which explicitly give you these kind of non-trivial co-states, weakly or partial Markov categories, or just categories of modules, or things called effectuses in partial form. But the key is that we've got these co-states, we form their tensor, and then we precompose by copier. So again, we have this precompose by copier situation, and we're going to have another sort of decorated something situation. Here we've got decorated co-spans, because we're going to decorate like co-spans of objects with factors, just to be decorated spans of something like objects before with sections. But previously, if you look in the paper, you'll see that the construction I make doesn't really make use of the whole double categorical machinery, because I don't require in the previous case the decorations to depend on the whole span. But here I'm going to want my decorations to depend on the whole span. The whole span is going to be made up of something like this, which I'll tell you about in a minute. And you'll see why I need the whole span in a moment. Okay, so the factors, the domains of these factors are like finite tensors of objects. So we take finite sets, and these are going to represent like indexes of my objects, and I decorate them by sort of type information, which are just functions into the objects of some category. And then a co-span encodes which objects are exposed for composition. So then we've got a double category of co-spans. The vertical morphisms are just functions. I decorate these with comonoid homomorphisms in my category that I'm starting with, where the factors live. So these are deterministic functions, and we need this homomorphism property so that it can be copied, because I want to do copy composition along these vertical morphisms. Then we've got co-spans, so they've got two legs and an apex, and we decorate the apices with both interfaces, which are these type decorations, and then factors on the tensors of these decorations. So then we've got this kind of double decoration thing going on. And decorating usually is a sign that you've got a gradient deconstruction, and indeed we've got sort of two gradient deconstructions, one over another. And then, okay, there's a lot of stuff going on, but we have these now squares, but now we've got morphisms in the apices as well. But we need them to project out to deterministic functions on the legs. And that's why we have this dependence on the whole span structure, because we need to look at the legs to say, okay, which bits are deterministic? And then, okay, that gives you a kind of way to say, okay, well, I've got deterministic morphism exposed bits, but not necessarily deterministic morphisms between the decorated factors, between the factor decorations in the middle. And this gives me my whole double categorical structure, and it's in detail in the paper, of course. And to see why you need this common homomorphism, it's basically, as I said, you want to compose along these, like these determinists along these transformations of the interfaces. But we need to be able to pull these transformations through the copier, which means that they have to be comonoid homomorphisms. So that's easy. But the nice fact of this double category is that we can have like non-deterministic transformations on the unexposed interfaces. So you can do things like marginalization, which is something that you often want. You don't necessarily want to keep all of the things around. And that would be just put a state on your hidden part. And I guess I should finish soon, but I've got some nice kind of ideas about graphical calculus, which kind of recapitulate some of the stuff that you see in the literature. It's only in the appendix of my paper, but the idea is that we have these kind of bubbles, and we sort of compose them with these spiders, like you see in the sort of quantum information theory work. And if we've got a sort of deterministic thing, I write it with a sort of pointy box, you can sort of pull it through a spider. And you can sort of draw a bubble around like your network, and then if you've got a deterministic thing, you can sort of pull it outside of the bubble. So this is a kind of a graphical way of representing these things, which are often graphical in the literature. And we can recapitulate quite easily the thing we started with, and it's quite this form. If you look at this and you look at some of these factor graphs you see in the literature written by people, they often have exactly, well, not quite exactly, but almost exactly the same kind of depiction, which is obviously nice that you're sort of recovering the thing that people do informally. I say informally, but this sort of double undirected wiring diagram calculus isn't formalized. It's not what I was doing. I was just kind of thinking about copy composition and modeling. So it'll be interesting to see people work on double categorical wiring diagrams. I'm sure people are thinking about that. And so, okay, that's it. That's copy composition in these two cases. We had directed ones and undirected ones, and they were kind of different, but they were both formalized by this kind of Graham deconstruction, which associates models in some sense to like types or interfaces and composes them by this copy composition method. One thing I sort of started thinking about when I was thinking about this problem was that it would be nice to have amongst the undirected models, the directed models, in the same way that you get amongst relations functions. You can sometimes think of kernels as like enriched relations, and I guess in this enriched setting you get a similar thing, but this isn't the right setting to do this. You would need to work with more like this enriched relations setting. And I guess in that context, you may get directed models or directed things amongst the undirected ones, but they wouldn't necessarily be like these models. This is really about sort of building up the models that you see in literature. And as I say, it'd be nice to have this kind of 2D calculus for undirected wiring diagrams. One thing we'll hear about later in the conference is kind of belief propagation. Belief propagation is like a thing you do on a factor graph in some sense to compute like approximations of the distributions at the nodes given some constraints. And one of the things I was thinking about when constructing this double category is using this thing for inference, for doing this kind of approximate inference by algorithms like belief propagation. And I hope that structures like this might be useful for that. And that's all. Thank you, everybody.
Okay, let's have some questions. Yes, please.
Hey,
Yeah.
thanks for this talk.
Cool.
Love seeing your factory ideas.
Yeah.
Can you go back to slide 7, please?
Slide 7, yes.
Sorry about
No, that's fine.
that. So maybe then it's about the fiberwise.
Yeah.
So then I'm considering this in the context of world spaces.
Yeah.
It's actually quite subtle.
Go ahead, speak up.
Yeah, it's actually quite subtle.
Yes.
The reason is that at some point you might want to be taking the direct image
Yes.
of the Borel set and the projection.
Yes.
That's not necessarily Borel.
Yes.
It's only considered with that potentially a gap.
It's potentially a gap.
Okay, so we can.
Yes.
Thanks.
There are lots of things which one might want to make a little bit more precise. I'm working also in this very general setting. You don't necessarily always work in that general setting. I was also interested in this kind of like dependent product structure. There's lots of questions about like making this like as nice as it could be. Yeah. So I haven't got answers to that, but I would like to have yeah. Okay.
All right, there's 2 more questions. All right, let's start with one maybe.
I have a question I'm sure is on everyone's mind. In your factor graphs,
Yeah.
and so you make them do plate notation?
Well, you give me the I don't know the two-dimensional stuff, and maybe I don't know. Yeah, I know it's a thing that people as we've seen. So I don't know. Yes.
All right,
Oh.
Owen.
Could you comment on the relationship between this and Copera?
Oh, yes. So when you say this, do you mean this or the previous one, the direct?
The direct.
Yeah, it's pretty much exactly a Copara thing. You can write it, yeah, you can write this as a kind of dependent Copara, and it gives you exactly the same double category. But another thing I wanted to do was come to the conference and say, hey, Evan's work on double decorated cospans was really useful for this.
Okay.
And that's not the same. One thing I think is that this story of double grid deconstructions for decorations, blah, 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 is more general than the Copara story because of the fact you can have this dependence on both legs. So in this case, as I said, I have trivial decorations on the legs, and that makes it relatively easy to do the decoration, the sort of Copara thing. But when I was working through doing that, I didn't see a way to do. What I wanted was a theorem to say, oh, like these double decorations are the same as Copara, but it's not. I think I can always show a like a Copara thing of some form gives you a double decorated thing of this form, but I don't have an implication in the other direction. Yeah, but I haven't written that down. Yeah, as always. Cool. Yeah.
Right on the post.
Thank you. Any more questions?
Does it mean to pull out of the double?
Oh, right. Yeah. So here I'm just saying I want to consider this as a factor, and I've got this factor which I'm considering as this composite network, and I have like a 2-cell which allows me to sort of reveal the fact that inside it is a factor, but it is made up of this composite with this morphism on this exposed edge. It's just a way of saying that it's kind of a way of depicting the naturality of the horizontal composition. Is that?
What's the squares?
Oh, the squares, I drew them because the diamonds can I thought that you can sort of puncture a hole in the bubble. So they're the deterministic ones. So you can, like in biology where you have some molecules that can get out of your cell. And these ones, they're too flat. They push up and you can't get out. So these are the non-deterministic ones. Yes, but that's not formal.
We made sure that
Yeah, it's very annoying in text. I just used diamonds and squares and oriented them. Yeah.
Okay, any more questions?
Nope.
Yes. Okay.
Could you say something more about, you started with string diagrams and then you're like using operads for the factor graph?
Yeah. Well, you mean string diagrams here? Or
Yeah, you just mentioned operads in a positive way.
oh,
To give you more.
I said operad, but actually I don't like saying operad. I meant multi-category.
Okay.
Or what people call colored operad. But yes, because you can nest a diagram inside another diagram. But I didn't present it like that. I presented it like this double. I guess it's a monoidal double category, and it probably corresponds to some double operad algebra. There's something underlying your question, I thought.
I think that is a big future direction. And
Yeah, well, that's
the fact that it's useful to you. I think it might be useful to others.
Yeah. I mean, this is an example of, I think, of one of those. Yeah.
Yeah.
Again, not proved in the paper, but yeah.
Thanks.
One last question, anyone? Okay, so let's thank our speaker again.